So this lesson is an introduction to the topics of photons and lasers. The first thing we're going to look at is photons. When we think about light, it's sometimes useful to think of light as a wave. It has many properties of a wave. For example, it reflects off of surfaces just like waves do. It refracts, that is, it changes its direction or bends when it passes from one medium to another. It has a frequency and wavelength and amplitude. The frequency is what determines its color. So in many ways, light does in fact behave like a wave. At the same time, light also has properties that we think of more as a particle. So sometimes it's helpful to think of light as little particles of light, and we call these particles of light photons. This idea that sometimes we think of light as a wave and sometimes as a particle is called the wave-particle duality. Duality has that word dual in it. That means two. So a duality is a situation where you have two things coexisting at once. So photons, we think of as particles of light, also have properties of waves. So there's really two different ways of looking at light. We've talked a lot already about the properties that light has that make it like a wave. Let's look a little bit more now about the properties of light that make it like a particle. So one thing that's true about photons, these particles of light, is that they can interact with other particles, sort of similar to the way that billiard balls can interact with each other. When one billiard ball hits another, it can change its motion or its course. So if we have a photon that has exactly the right amount of energy, the right wavelength, if it's just the right amount, that photon can actually interact with an electron. What can happen is that the photon comes in, and if it has just the right amount of energy, it can kick that electron up to the next energy level. Remember that electrons existed in energy levels or shells, and if we add some more energy to that electron by hitting it with a photon, that electron can actually jump up to a higher orbit. What then happens, eventually, that electron falls down to the lower energy level. When it does that, when it falls back down, it's releasing the energy that it had taken to kick it up to the higher level in the first place. So when that electron falls back down, it actually gives off a photon. That extra energy is released as a photon. Next, we're going to look at something called an absorption spectrum. So suppose that I were to create a complete rainbow. That is, I were to take white light and send it through a prism so that it was refracted out into all of the different colors of the rainbow. If I were to shine this rainbow through a cloud of gas molecules, those gas molecules have electrons at particular different energy levels. And what would happen is that those different elements are going to absorb certain frequencies of light. Certain color photons are going to get absorbed. And which ones get absorbed depends on the electron configurations of the particular elements in that cloud of gas. What happens then is we have these black lines, these missing bands of color. So for example, in this case, we have a bunch of missing black lines in our spectrum. One of them on the far right-hand side is in the reddish range. So there's a particular frequency of light that got absorbed by this gas. The location of these lines, it's like a fingerprint. It can tell us what elements or compounds make up that gas. So we can tell just by looking at the pattern of those lines what the material is that the rainbow is shining through. This also goes the other way. So an absorption spectrum is a spectrum where we have all the colors of the rainbow present, but a few of them get absorbed out. This can work the other way as well, when we emit only certain colors of light, and this is called an emission spectrum. Let's say that we have a whole bunch of molecules, and the electrons in those molecules have all already been kicked up to those higher energy levels. As those electrons fall down to their lower energy levels, they'll give off photons of a specific wavelength, and the wavelength they give off depends on the difference between their energy levels when they fall back down to that rest state. So the wavelength of that photon depends on how big that energy jump orbits is. we have in this case is we have bright lines. This is where those electrons falling down to a lower level are giving off photons at a very particular color. And we can tell by looking at where those bright lines are in the spectrum what element is giving off those photons. So what's shown here, for example, are the emission spectra is the plural of spectrum, for a variety of different elements. You can see in the top that hydrogen emits light at one red frequency, a green, a blue, and then two that are sort of in the violet range. Neon, on the other hand, emits light primarily in the red and yellow end of the spectrum. So each element has its own particular emission spectrum. This is how we can tell what elements are present in very faraway stars, even though we can't take samples of those faraway stars and analyze them. We can look at the emission spectrum of their light and determine what elements or compounds are present there. So a way to summarize this, we have this light bulb here that's emitting white light. That white light is going through a prism and being bent, and we see a continuous spectrum. That is one that has all the colors of the rainbow in it. If we were to take a hot gas instead of a light bulb and pass the light from that hot gas through a prism, we would see those bright lines only at specific colors that correspond to the elements within the gas itself. On the other hand, if we were to take the light from the white light bulb and filter it through a cold gas, that cold gas is going to absorb some of the specific frequencies, and so we'll have some black lines or an absorption line spectrum.
In the 1850s, Robert Bunsen and his research collaborator Gustav Kirchhoff conducted a series of experiments to determine why substances emitted specific colors when placed in a flame. The color they determined indicates what elements are present in the substance. For example, if sodium is placed in a flame, they observe shades of yellow. Copper, shades of green. Strontium, shades of red. That was a good one. While watching the experiments, Kirchhoff was reminded of how a prism spreads light into a rainbow of colors. So, using a prism and the pieces of a small telescope, Bunsen and Kirchhoff built the first spectroscope, an analytical device they hoped would help them see the spectra coming from heated substances. And it worked. As an element was put into the flame of a Bunsen burner, the light from the heated substance passed through the prism of the spectroscope, where it then spread into a ribbon-like spectrum of colors, riddled with dark lines. The combinations of bright colors and dark lines were like barcodes indicating what atoms were present. When burned, each element produced a completely unique spectrum. Using their spectroscope, Bunsen and Kirchhoff were able to discover two new elements, cesium and rubidium. One day, Bunsen and Kirchhoff decided to test their invention with sunlight. It produced a spectrum that featured two lines that were identical to those in the spectrum produced by sodium. Bunsen and Kirchhoff had discovered the presence of sodium in the sun, 93 million miles away. Suddenly, scientists had a tool to help them study the chemistry of the heavens.
Liftoff. We have liftoff.
Today, the legacy of this great discovery lives on in the exploration of space. A form of spectroscopy is being used to study the atmospheres of planets, to search for signs of water, signs of life.
The next topic we're going to look at is lasers. The word laser is an acronym, and it stands for light amplification by stimulated emission of radiation. So let's look at each of those words individually. Light, we know lasers obviously give off light. It comes in different colors, but we're talking fundamentally about light here. Amplification means to make bigger. So an amp, like a guitar amp, makes the sound bigger. In this case, it's the light that we're going to amplify. The stimulated emission of radiation, stimulated means we're going to force it. Emission means to give off. So we're going to force something to give off some radiation. Now this isn't radiation like X-rays or gamma rays. This is light. So we're going to stimulate something to give off light. Let's look at the characteristics of the light that comes from lasers. First off, laser light is monochromatic. Mono means one. Chromos is the root for color. So monochromatic, all one color. It's key to note that the light coming out of a laser is all exactly the same color. It's all exactly one wavelength. Different lasers have different wavelengths, but any given one laser will only produce light at one color. So a green laser will only produce green light. It won't adjustable to produce red light or any other color light. It only gives off light at that specific wavelength. The other thing is that the light waves are what we call in phase. This means that the light waves are lined up so that all of their crests line up and all of their troughs line up. This means there is very significant constructive interference. Remember, constructive interference was when we took two waves and added them so that their crests lined up, and that amplified the wave. It made the resulting light wave much taller, much brighter. This is the amplification part, the A in laser. The other thing that's key about lasers is the light waves are all aligned. They're all pointed in one direction. This is different than, for example, a flashlight. So if you shine a light from a flashlight, you'll see that as the light beam coming out of the flashlight gets further from you, the beam gets wider. And this is not true of a laser. All of the light waves coming out of a laser are in parallel and point in the same direction. So lasers don't diverge as they go farther away. Practical uses in day-to-day life. Things like LASIK eye surgery. The L in LASIK stands for the word laser. This is a way that we can very carefully and very precisely reshape portions of people's eyes to give them better vision. There are a lot of applications in manufacturing settings where we use lasers to very precisely cut or melt things. The piece of bread shown above with the word "stupid laser tricks" burned into it is actually simply a demonstration of the fact that if you have a laser mounted on a very precise arm, you can have it write words by burning the letters into toast. It's kind of a silly thing. The picture in the middle is a picture of what was at the time one of the largest lasers in the world. It was a laser where they took multiple beams and concentrated the laser light down to a very small point to create exceedingly hot conditions at that one point. To give you a size of how big the lasers in that center picture are, you'll see on the right-hand side there are some blue boxes with some gray tubes coming out of them. The tubes contain the laser beam. To get a sense of how big those laser beams are, if you look right about in the middle of the picture, you'll see a little orangish thing. That's a forklift driver with a person standing in it. So each of those laser beams is about a foot tall. This was at a place in California called the Lawrence Livermore Labs in the early 90s, and at the time it was the biggest laser there.
Laser light is a very special type of light with a number of unique characteristics that allows it to perform a variety of spectacular tasks in science, industry, medicine, and entertainment. Laser stands for light amplification by stimulated emission of radiation. Albert Einstein theoretically proposed the existence of laser light about 1920, but it was not until 1960 that the first lasers were developed. Laser light is produced by stimulating the emission of photons, or packets of light, in different substances such as helium and argon gases. In this argon laser, an electric current stimulates the electrons of the argon gas and causes them to emit a blue light. This blue light is reflected back and forth by mirrors at either end of the laser. The reflection of photons causes the release of even more photons by the argon gas. One of the mirrors is 100% reflective, while the other is only 98% reflective, allowing some of the light to escape and form a laser beam. The ordinary white light emitted by the sun or a light bulb is a mixture of light of different wavelengths and frequencies, traveling in a variety of directions. Laser beams are made up of waves of light that are all of the same frequency and traveling in the same direction. In addition, waves of laser light are all in phase, which means that the waves amplify one another. This quality explains the ability of laser beams to cut and weld heavy materials such as iron and steel. The narrow focus of laser beams allows them to be used as measuring devices on construction sites or to provide a precise reference point for the realignment of automobile bodies damaged in accidents. Lasers like this one in Parkfield, California, are used to measure the movement of the Earth's crust along the San Andreas Fault. The highly focused nature of laser light allows it to be used in a number of medical applications, such as eye surgery to replace detached retinas and remove various types of skin lesions. Laser scalpels allow general surgery to be done with less blood loss, as laser scalpels cauterize wounds as they cut. A technique called LIDAR, which is similar to radar, uses laser light to track the flow of pollutants through the atmosphere and to detect a phenomenon called wind shear that is a potential threat to all types of aircraft. Beams of laser light can also be used to scan barcodes from products in supermarkets and department stores, as well as to read the digital information stored on compact discs, CD-ROMs, and laser video discs. Laser light is also used to produce spectacular laser light shows. Television signals carried through fiber optic cables on waves of laser light hold the promise of over 500 cable channels in the near future. Light provides not only the basis of life on Earth, it also adds exciting and spectacular images to our existence. To understand the nature of light is to understand one of the most dynamic and powerful forms of energy in the universe.